As we look here at notes number 4 for this year, I don't think it's very difficult, but I think there are some things that we want to make sure that everybody understands before we really move deeper into the unit. As we look at this first example, I think this is pretty easy because of where we've been so far this unit. If we look at this, let's go with Harrison on this one. Hey, Harrison, how you doing today? Super. As we look at this, think rice chart. Are we going to go to the right or are we going to go to the left to achieve equilibrium? To the right. And why is that? What did you see? The zero, this zero drives everything. We know if molarity is what goes in the rice chart, you cannot go down from zero molarity. It's got to go up. Since that has to go up, the whole side has to go up, and then the left side goes down. Now, Allison, I look at that and I keep boycotting H2O in the rice chart. Why do I not have a down by, up by, or a molarity there? Pure solids and pure liquids do not appear in the equilibrium expression. They're important for the chemistry, but in terms of the rice chart, we do not do anything with the H2O. Okay? Let's talk about what buffers are. If I were a student, I would be saying this. Buffer problems, which we've been doing, you start with two things, like 2 molarities are given. That I know. But also, you could do them as a Ka, or you could do them as a Kb problem. But here's the sound bite that I want you to truly memorize. This, I believe, is important. And I'm going to write memorize. That is one of the big ideas of the overall school year. All right? And when I say memorize it, yeah, you may get a little bit rusty in terms of your calculations of buffer types of calculations by the time February or March rolls around. But knowing what a buffer is, I think there's tremendous value in that. Okay? Buffers are combinations of weak acids and weak bases that resist changes in pH. All right? And you're going to see, well, we're going to talk more about what that means. Okay? Now, to me, if you look at the buffer combinations that are listed, why, here is my weak acid. There's a Ka value for that. Here is the corresponding weak base, or as we might say from notes number 1, the conjugate base of the weak acid. Okay? Over here in the other example, here is a weak acid, ammonium, and its corresponding weak base, ammonia. We know we've done lots of problems with these two buffer type of systems. What I say here, differ by a proton, it means this. Hey, there's a hydrogen there, but it's not there here. Where'd it go? It's gone. Okay? Here's an extra hydrogen. It has the extra hydrogen. You take that away, and you have the corresponding weak base. So there's an extra proton on the weak acids. All right? They only differ by a proton. Buffers are all around us in our world. Okay? I used to believe that, it's some chemical concoction that you create in a beaker. There are buffers in many of our food products. Many of our medications, in an aquarium. There is the fish water has a natural buffer that is established in it. Okay? The fish buffer is actually this right here. The ammonium system is alive and well in any functioning fish bowl. Okay? With the waste that the fish produce, it's in equilibrium. And depending on the pH of the system, you've got your ammonia, your ammonium ion, and it resists changes in pH. Lemonade mix. Lemonade mix contains citric acid as well as sodium citrate. The same is true of our orange juices that we might buy. There's fresh squeezed orange juice, and then there's the other stuff that you can buy where, wow, this doesn't expire for like 3.5 weeks. That's awesome. It's got a longer shelf life than milk does. And if you read the fine print in the ingredients, yes, indeed, there's natural citric acid present in oranges and lemons and things, but they also add sodium citrate to that to maintain a fairly constant pH. That pH could be pH 5, pH 6, somewhere your juices would probably be in the slightly acidic range, okay? And it's going to maintain that pH, because when the pH changes, the taste is different and it starts to decompose. Or you go, ooh, it went bad. Ooh, yikes. The pH really, really dropped, or the pH rose, okay? So we want it to stay fairly constant. The way I like to think about buffers, and unfortunately, if you're watching from home, you're not seeing this, but I've got a pH meter, pH sensor, if you will, that we've been using for some of the labs in front of us. And it reminded me earlier today of when people in the 1980s, actually, I think this is a 1980s thing that extended into the 90s. In college football especially, if there ever happened to be an upset, where, say, Alabama loses to Kent State or Bowling Green or some major upset, it became a college tradition to tear down the football goalposts. And I'm not sure why or who thought of that, like, let's destroy our own field, but it happened. And so you would see sometimes Northwestern University would knock off a top-ranked team, and all of a sudden you would see, and they would show it on TV, like, uh-oh, there goes the goalpost, and you would see people up on the goalpost swinging back and forth, and people pushing, and then all of a sudden, down it goes, and it was almost like a celebration. Yeah, we destroyed our own field. And it was crazy. Well, then in the 90s, I think they decided we're tired of replacing the goalposts, and people could get hurt. And I'm sure people were hurt, either falling from that height, or I was just standing there watching it, and all of a sudden it came and landed on me, and ouch, that hurts. So what you started to see, and I remember my wife and I going to an Ohio State football game where we beat Penn State. And this is back in the 90s when Penn State was way up there and didn't know if we were going to win or lose and all that. And Penn State's kind of had a return here this year to glory. But here's what the law enforcement folks would do at the very end of the game. They would basically say, all right, we need about 50 of you at each end of the stadium. And as soon as the scoreboard, the clock goes to 0, you are going to form a human chain, a human barrier around the goalpost. And you guys can link arms like we're in riot gear or whatever. No one is going to get to the goalpost. Now, I had some students earlier go, well, yeah, but I mean, if they're all the way there, couldn't you just jump up on the crossbar? No, it was a big enough circle, and you were not going to get there. I want you to have that image in your mind as you think about a buffer. Because a buffer says you're not touching that pH. I said it's going to be 5.60. Oh, you can add acid at pH 1 if you want, or base at pH 14. That reading is still going to be 5.60 because it's a buffer. The buffer is going to defend the pH reading. It's not changing. It's going to stay 5.60. That's how buffers work. Now, if you think about protecting, and you're not going to get to touch that because we've got, all of the acids and bases lined up, it makes, I think, a lot more sense. If you think about your law enforcement folks, if there's 500,000 and 500,000 on each end of the stadium, you're not going to get to either goalpost. You're not. It's well protected, it's balanced. Your best buffers have the concentration of the weak acid and the weak base are about the same. So that's better. okay? And I'm going to say if they're each 0.5 molar, that's good. You're well protected, okay? Now that's in contrast to what we see here, where we've got 0.5 molar weak acid, but only 0.1 molar of the weak base. So clearly we don't have as much out here to protect or defend the goalpost or the pH meter, okay? We've got some, but they're not going to be able to hold on for nearly as long as the 0.5 molar weak acid, all right? So ideally we want the pH, or excuse me, the molarities of the weak acid and the weak base to be about the same. This part here is new today. And again, my hope is that all of you leave here today saying, I think I have a better understanding of what you mean by a buffer. If we look at this chemical reaction here, this buffer, this is my weak acid, and this is my weak base. What I know, and I've tried to leave space underneath for us, but here's what I also know. Acids react with bases. It's always the acid and the base react. The base and the acid react. But we never talk about, and there are reasons for it, this acid reacted with that acid. No. Or this base reacted with that base. No, no, no. It's always an acid reacts with the base. And if you keep that in mind, and you probably already knew that, if you keep that in mind, what I'm going to show you here, I think makes a lot of sense. If we add a strong acid, like HCl, which is a delightful source of H+. If we add H+ to a buffer, here's what happens. Again, picture everybody defending the goalpost. The weak acid and the weak base are protecting the pH. If you add H+, here's the reaction that occurs. H+, being a strong acid, is going to react with the weak base. It's going to be a single arrow because we're dealing with a strong acid. So I'm going to write strong acid. And this is a weak base that's in the buffer. And it's going to stick together to make a weak acid. So you will convert some of the weak base gets converted into HF, which is a weak acid and is part of the buffer system. Well, let's say that you decide, you know what, I'm going to add hydroxide, a strong base, like maybe potassium or sodium hydroxide. No problem. The OH minus, being a strong base is going to react with the weak acid, and that's going to produce HOH plus F minus, which is more of the weak base of the buffer system. So if we add base, it reacts with that and makes it into more of the F minus. So to me, this seems really, really logical. Acids react with bases. Now here's an analogy that I thought about this morning, okay? When a student said, so wait a minute, you said the pH is going to be 5.6 or 6.5 or whatever. And you're just going to add like hydrochloric acid with a really low pH, but you said that the buffer pH doesn't change. That just seems almost impossible. I want you to watch the sponge here at the sink. There's a little bit of water. flip it over. Ooh, magic. The water goes in, but no water goes out. The strong acid comes in. Oh, you can charge the law enforcement folks standing around the goalpost. You will not reach the goal. No, you will not. If you're like me, you're like, you're talking a big game there, Bracken. How's that working for you? Oh, no! Oh, no! Well, a lifetime of experience tells us, dude, the sponge can only hold so much before you've overwhelmed the absorbance of the sponge. Look, it's still leaking! Right. Yeah, you need a bigger sponge. Well, here's what I want you to do. Please flip the whole set of notes onto the very back. Flip over onto the, I'm going to do the same. Buffer capacity. Buffer capacity, they did a great job of naming this. Because if you understand the idea of if you add a small amount of water, the sponge can handle it. If you add a small amount of acid or base to the buffer, it just looks at you and says, not changing. I'm not changing. No, I'm not changing. If you decide, fine, think you're Mr. Hot Shot Buffer, how does 250 mils of 12 molar HCl sound to you? You have blown out the buffer. That's what we say in the business. You've blown it out. Well, what do you mean? I added some of the strong acid. You added so much strong acid, I didn't have enough weak base to react with it all. You blew it out, okay? I don't have any more weak base to react with what you're adding. You've exceeded the capacity of the buffer. If we think of it like this, 0.1 molar, 0.1 molar, let's convert molarity. Think of that as like millions. If you have 0.1 million here, 0.1 million there, and suddenly you dump a whole bunch of acid onto it, or the fans in the stadium storm the field, and you're like, there's only 50 police officers there. 109,000 of us here in the horseshoe. Well, you guys go first. Okay. Again, think of it. You've got a 0.1 million protecting. Now you've got 1 million protecting. This, to me, clearly has a larger buffer capacity. Okay? It's going to be able to accommodate maybe 5 or 6 or 7 or 10 or 20 milliliters of outside attack before that pH changes substantially. Okay? They did a great job of naming it, in my opinion, here. Buffer capacity. How much can you handle before the pH changes drastically? Okay? Buffers will fight it, and then eventually you have exceeded the capacity of the buffer, much like the sponge. Okay? So that's buffer capacity. What I'd like for you to do in the last 5 minutes here is let's go back, and I want you to do this. Buffer example number 1, which you should be able to do either way, and I've discovered today some folks are still locking this in. What is the pH? What is the pH? It's 0.32 here, 0.13 there. I give you the Ka. But here's the deal. I want you to prove that you could do it as a Ka. And some of you might say, well, that's how I do every buffer problem. Then do it that way. But I also want you to do it, again, as a Kb problem. And you will get the same answer. Okay, this is the final answer. Don't use that in your answer or to solve the problem. It's easier than I think we did the problem at the start. Okay, do it as a Ka, do it as a Kb. They don't look anything like each other on the way to the final answer. But if you do it right, no matter if you did it as a Ka or as a Kb, you'll finish with 4.36 as your correct pH value. Okay? And we will finish the rest of the notes here tomorrow.